Welcome to your first class in digital electronics. My name is Aaron Dahlin, and it is my absolute pleasure to be your instructor today. To get started, we are going to do a class review. From there, we'll review Ohm's law and power laws, and then we'll discuss the LED and the transistor. Essentially, we're starting at the output of our integrated circuits, and we're working our way in. Our class will follow this general outline. Today, we're starting on the digital interface. In our next lesson, we'll pick up number systems. Next is combinational logic. That includes a discussion of the logic gates, as well as simplification using tools such as K-maps. Next is the sequential circuits, and those are circuits with memory. From there, we'll discuss things such as data path components, an exploration of hierarchical designs, and finally, time permitting, we'll do an introduction to Verilog. There will be 4 exams. Exam 1 is approximately these topics. Exam 2 will certainly cover all of the combinational logic. See, there's a little overlap there. Exam 3 will be dedicated almost exclusively to the sequential circuits. And finally, we'll have exam number 4 to catch everything else. And if you're curious, yes, exam 4 is cumulative, as you certainly can't talk about data path or hierarchical design without knowing about combinational and sequential circuits. There are labs in this class. We start with hands-on construction of traditional logic circuits. We then move to an FPGA. We'll actually use the Quartus platform. We'll likely do some simulation using online tools such as CircuitVerse. And we may do a little bit of simulation using Multisim Live. With that said, let's begin with a review of electronics. Specifically, Ohm's law and power. So voltage, current, resistance, there's a relationship using Ohm's law, and power, current, and voltage, where voltage over here on Ohm's law is current by resistance, a current is a voltage divided by a resistance, and a resistance is a voltage divided by a current. On this side, power is equal to a current by a voltage, current is equal to power divided by voltage, and finally the voltage is power divided by current. And I believe you've seen me do the cover-up method many times before. If we put all of this together, we can say that power is equal to IE is equal to I squared, R is equal to E squared divided by R. Here's an example. A 12-volt supply, a current meter, and a 3-ohm resistor. Solve for the unknowns. In this case, the current is measured by that amp meter is a voltage divided by a resistance. In this case, it's 12 divided by 3. So that current is 4 amperes. The power is voltage squared over resistance. So that's 12 squared over 3. So that's 12 times 12 divided by 3. So that's 48 watts. All right, no worries there. Here's another example. We have a battery of unknown voltage, a current meter that reads 2 amperes, a resistor such that the heat given off by that resistor is 3 watts. Solve for the unknowns. Voltage is equal to power divided by current is equal to 3 watts divided by 2 amps. Therefore, the voltage is 1.5 volts. Power is equal to current squared by resistance. Rearranging that equation, we see that resistance is equal to power divided by current squared. In this example, that's 3 divided by 2 squared. That's 3 divided by 4, which is, of course, 0.75. By the way, there's this SD button, which is kind of nice on your calculator. So resistance is equal to 0.75 ohms. This is all well and good. However, something we need to do is we need to ask ourselves, is that resistor value actually available? Turns out there are standard values for resistors. There is the E6 series, which we would recognize as resistors having a 20% tolerance. There's also an E12. Those are the 10% tolerance resistors. And the E24, which are 5%. Actually, this does continue on, and you can get resistors that are even tighter in tolerance. But for our purposes, we'll stick with this E24. To better understand what this E24 value means, let's shift over to Wikipedia. On this page, we find the E series of preferred numbers, and we're going to scroll down to find a table. Here we go. So here's the E6 values I mentioned. Those are the 20% tolerances, the E12 with the 10, and the E24 with the 5% tolerance. Notice that there are 6 values in the E6 series, 12 in the E12, and 24 unique values in the E24 series. Now that's 24 values per decade. And when we talk about a decade, we could look at this number right here, for instance. So 7.5. If you multiplied that by 10, you would be able to find a 75 ohm resistor, or a 750. Or back to our original problem, you would be able to find a 0.75 ohm resistor. We can check for availability by using a parametric search engine provided by distributors such as DigiKey. So we enter resistor, and we specify through-hole resistors. This is the parametric search engine for our through-hole resistors. Here are all the parameters that you can choose from. For this example, we'll choose the power rating first. Remember that our design actually had a power rating of 3 watts. We're going to choose something a little bit higher than that to allow some additional wiggle room. Generally, you don't want to run the resistors right at their power rating, so we'll select something between 5 watts and 10 watts. And then as far as tolerance is concerned, we'll select a 5% tolerance. Now we can scroll over and look for our resistor of interest. And we said 75 milliohms, apply all. So here are the resistors that we could potentially use. This first one is a 5 watt resistor, and these other two are 10 watt resistors. All 75 milliohms with a 5% tolerance. Just a reminder, when we said this was an E24 series, that meant there were 24 unique values per decade. For example, you could buy a 2.2 ohm resistor, a 22 ohm resistor, a 220 ohm resistor, a 2.2K, and so on and so forth. And of course, you could go in the opposite direction as well. You'll notice there is a decade, a multiple of 10 between each of these values. Our next topic is the ability to interface with digital logic. One way to do this is to have your delicate digital logic circuit directly drive a load. Your typical logic circuit will be connected up to a 5-volt source. and will also be connected to ground. If we're careful, an output terminal from this integrated circuit can be used to directly drive a load. Internally, you could think of this as a switch that is either connected to the 5 volts or it's connected to ground, and this is your output, with some control logic inside to determine where this switch is going to be positioned. Regarding this voltage here, at one point 5 volts DC was very common. Today you're likely to encounter 3.3 volts, 1.8 volts, and occasionally 1.5 volts DC. In this class, we're going to be dealing with 5 volt components and 3.3 volt components. Back to our stick figure here, 5 volts DC would be considered logic high, and 0 volts DC would be considered logic low. So a high would be considered on, a low would be considered off. A typical example of this type of load connection is driving an LED, a light emitting diode, where we're direct connected. Here is our digital logic circuit. This time we'll let the rail be 3.3 volts DC. Of course, there will be a ground in there. To the output pin, we'll connect a resistor and an LED. For this example, we'll let the LED have certain characteristics. At 10 milliamps, the forward voltage as measured on the LED is 1.9 volts DC. Which means if we were to put a voltmeter here, when the digital logic is on, this would read 3.3 volts. And if we were to put a voltmeter here, we would read 1.9 volts. Your objective is to find the value for this resistor. So R is equal to a voltage divided by a current. In this case, it's 3.3 minus 1.9, because we're interested in the voltage drop across the resistor, and we specified a current of 10 milliamps. So that's 3.3 minus 1.9 divided by 0.01. So R is equal to 140 ohms. But is it? Because again, you have to ask yourself, can we purchase that 140 ohm resistor? And of course you can, but it might cost more money than you want. So a better question is this an E24 value? And the answer is no. 140 ohms is not a standard value for the E24 series. You could use a 130 ohm or a 150 ohm. So we don't use 140, we specify either 130 ohm or 140 ohm 5% tolerance resistor, because 5% is the E24 series. While we're here, we should calculate the power on that resistor. So power on the resistor is equal to 3.3 minus 1.9, all multiplied by 0.01. That's 3.3 minus 1.9. So that's the voltage drop across the resistor, multiplied by the current that's flowing through the resistor. Allowing a factor of 2 safety, we could select a quarter watt resistor. So 130 ohm, 5% quarter watt would be just fine. Now, we have to be very careful with our direct connections. Our integrated circuits, these digital devices, are very delicate. They can only handle a certain amount of current. For example, if you were connecting up to a Raspberry Pi, which is a popular microcontroller, you would be limited to about 16 milliamps. In Arduino, at least the Arduino Uno, you got to be careful on your models, but the Arduino is somewhere around 40 milliamps. A old 7400 series logic is somewhere in the 16 milliamp range, and the FPGA that we'll be using in lab is again somewhere around 16 milliamps. This is good, but it's not the entire picture because this is a per pin basis. So an individual I/O pin, input-output that is, might be able to deliver 16 milliamps. But you got to be careful. Again, we mentioned a per pin basis. There's also a per device. For example, an individual pin on an Arduino may be able to deliver 40 milliamps, but not all of the pins can deliver 40 milliamps. So that's the difference between a pin and a device. If all the pins were to deliver 40 milliamps, you would end up damaging the actual device. You also have to be careful of the power supply as well. The power supply has to be designed and properly heat sinked to deliver that power. If not, you could damage the regulator. For larger loads, we need a buffer. Many different types. You could use a transistor, a MOSFET, that's an acronym for metal oxide field effect transistor. You could use a solid state relay. You might encounter optical isolation. And you may even find network-connected devices. An example would be an integrated circuit using a serial protocol to control something like a variable frequency drive, in which case that tiny circuit can control a multi-horsepower motor. For today, we are going to focus in on the transistor. A transistor is a three-terminal device. It has a base, a collector, and an emitter. For this class, we're going to use the transistor as a switch, and we're going to configure the circuit so that the transistor operates in forced beta. To understand forced beta, we have to consider the way the current flows through the transistor. Here's the collector current, here's the base current, and here is the emitter current. If you put this together, the emitter current is equal to the base current plus the collector current. In the forced beta configuration, we establish operating parameters such that the base current is the collector current divided by 10. So if the collector current is, say, 100 milliamps, the base current will be 1/10 of that, or 10 milliamps. When we talk about a transistor being a switch, what we mean is that a small base current controls a larger collector current. In this case, when we're operating in forced beta, there is a 10-to-1 relationship between the controlling base and the output on the collector. A couple of side notes here. The voltage base to emitter for the transistor while it's operating is approximately 0.7 volts. And the voltage collector to emitter is approximately 0.1 volts. In fact, for our purposes, we're just going to assume that that is 0. Going back to the transistor, the base to emitter voltage will be 0.7 volts, and the collector to emitter voltage will be approximately 0. Let's work an example to see if we can make some sense of this. This is the digital circuit. We'll let the rail be 3.3 volts, and of course ground. That digital integrated circuit has an output pin. We'll connect a resistor like so to a transistor. That transistor goes to ground, and there is a load on the collector of the transistor. We'll let this be 24 volts DC. Let's not forget the flyback diode. To turn the transistor on, the digital output needs to go high. When it goes high, the base of the transistor will be high, which means that the collector will be pulled towards the emitter. We looked at that another way. We would say this voltage here is 0.7, and this voltage, when the transistor on, is essentially 0. Let's assume that there is a 100 milliamp current in the collector. The base, because we're in forced beta, will be 1/10 of that, so that'll be 10 milliamps flowing in the base. Your job is to calculate this resistor value. So R is equal to 3.3, because that's the voltage here, minus 0.7, because that's the voltage base to emitter, and that is divided by 10 milliamps. So that's 3.3 minus 0.7 divided by 10 milliamps. So the resistor value is 260 ohms. Is that value available? No. I'll leave it up to you. But when you look up the E24 values, I think you'll find the closest value is actually 270 ohms. Well, that worked out pretty good. So we had a load in this case which consumed 100 milliamps, and we're able to reduce that by a factor of 10 using a transistor operating in forced beta. Remember, if we go up here, we have to be careful because there are limitations. There's a per pin limitation, there's a per device limitation. That's all well and good, but what happens when the current is greater than, say, 16 milliamps? Well, if we could use one transistor to reduce the current by a factor of 10, if you cascade two transistors together, we should be able to reduce the current by a factor of 100. Let's use a digital circuit. In this case, we'll run a 5-volt supply. The I/O pin is connected to the first transistor through a resistor. That transistor is connected to a second transistor. So we'll call this Q1, and we'll call this Q2 for transistor 1 and 2. Q2 is connected to the load. Let the power source be 24 volts. And don't forget the flyback diode. For this example, let the current be 800 milliamps. Using forced beta, the current on Q2 would be 80 milliamps. And again, using forced beta for Q1, the current here will be 8 milliamps. So you can see we've reduced the current by a factor of 100. This resistor, so R is equal to 5 minus 0.7 minus 0.7, all divided by 0.08. And that 0.7 drop is right here. So there's a 0.7 volt drop there, and there's a 0.7 volt drop there from the base to the emitter of the transistors. Looks like our resistor value is 450 ohms. Ask yourself if 450 ohms is available. It is not. So if we looked at the E24 values, the closest value is 430 ohms or 470 ohms. Not a bad solution. We took an 800 milliamp load, and using 2 transistors, we were able to reduce the current by a factor of 100. You could, if necessary, cascade 3 or 4 transistors together. Before we forget, do you remember what the voltage for this transistor is when it is conducting? And do you remember what the voltage is here when the transistor is conducting? For our purposes, this is approximately 0 volts. And this voltage here is 0.7, which is where these two numbers came from. 0.7 for each of the 2 transistors. Closely related to transistors are MOSFETs. That's the metal oxide field effect transistor. A very simple circuit looks like this. This is our digital device with a 5-volt supply and, of course, ground. Let the I/O pin connect to a resistor. The resistor connects to the gate of the MOSFET. And we'll let the source of the MOSFET connect to ground. The load is connected to the drain of the MOSFET. And then we'll go to our supply. So the parts are drain, gate, and source. And we're assuming we're using something called a logic level MOSFET. The MOSFET and the transistor do the same job, but they are different in how their respective control elements work. The MOSFET is turned on by a voltage. That's all this has to do. If this goes to 5 volts DC, this logic level MOSFET will turn on. There is very, very little current flowing here. So you could say that the MOSFET is voltage controlled, whereas the transistor has to have a current flowing in on the base. So you could say transistors are current controlled devices, whereas MOSFETs are voltage controlled devices. You'll notice that we still included a current limiting resistor for this MOSFET, and that's because it takes energy to charge the gate of the MOSFET. Essentially, the gate is a very large capacitor. So all that work that you did before when we talked about the step response of RC circuits, you still see that with the MOSFET. So in this case, you have the voltage gate to source will have an RC curve associated with it until it eventually charges up to the source voltage, which in this case was 5 volts. You should know that we've only covered a tiny, tiny fraction of the information there is to know about MOSFETs and transistors, but anything more is beyond the scope of our digital class. And so we move on to the relay. Once again, we start with our digital logic. In this case, we'll use a transistor, and we'll let that transistor control the coil of a relay. Let this be 24 volts, and we definitely want to get that flyback diode in there. If you don't have that flyback diode, you are going to destroy the transistor. This is the relay coil. We'll run a dashed line to a set of normally open contacts. This is the load. And just because we can, let's make this a 120 volts source. So in this particular case, we could use digital logic to activate a transistor, which activates the coil, which closes the contacts, which allows 120 volts to be applied to a large load, such as a motor. The last topic for today is the solid state relay. Here the term solid state implies that there are no mechanical or moving pieces inside the relay. You can purchase a solid state relay as a commercial off-the-shelf product. A typical device might have 2 screw terminals for the input and 2 screw terminals for the output. The input can be connected directly to your digital logic. Take an I/O pin, run it to that screw terminal, take the other I/O pin and connect it to ground. This is a really nice product because there's not a lot to worry about. Internally, the solid-state relay takes care of everything for you. As for the output, assuming this particular solid-state relay is designed for alternating current, you can connect your load there, and your 120 volt source would be connected like so, with this being the hot and this being the neutral. I should mention that these solid-state relays are available for either AC or DC. Internally, they all generally share the same construction. You're going to find an opto-isolator, which consists of an LED physically coupled to a transistor. And that transistor is then connected off to a power transistor or a MOSFET or a triac. Unfortunately, I don't have a solid-state relay to show you, but I do have a piece of a programmable logic controller that will show some of the same ideas. And here it is. What you're looking at is the output module for an Allen Bradley SLC 500 programmable logic controller. It's rated for 500 milliamps, provided the ambient temperature is at 30 degrees Celsius. And you can see the current rating actually drops as the temperature increases. Down here is a digital logic chip. This chip has multiple outputs going to these small devices here. These are the optical isolators. Inside there's an LED which shines a light across a gap to a transistor. The transistor inside the optocoupler then goes to this transistor here, which turns on the actual output. That transistor is very similar to the ones that we've showed earlier in our discussion. And so sensitive, very delicate logic is optically isolated to a heavy-duty transistor, which then controls the load. I mentioned that the output current of this device is reduced in higher ambient temperatures, and that's because the transistors themselves tend to heat up. If the ambient temperature is too great, the transistors will actually overheat and could be damaged. Well, I think that's enough for now. When you come back, we'll talk about computer number systems.